All right, please. Please be seated.
Hereby, I open this academic ceremony in which Lei He will defend the academic thesis Selenium-Incorporated Mesoporous Silica Nanoparticles for Oxidative Stress-Mediated Osteosarcoma Therapy. May I invite you to present a summary of your thesis and the conclusions.
Okay, thank you, Prorector. Dear Prorector, members of Corona, family and friends, good morning. Thank you for attending my PhD defense. In the next 50 minutes, I will present the work of my thesis, which is about developing the Selenium-Incorporated Mesoporous Silica nanoparticles for oxidative stress-mediated Osteosarcoma therapy. Well, first, I will start with what is the osteosarcoma. Osteosarcoma is one of the most common primary bone cancer, mainly affects children. It often occurs in long bone around knees, inducing pain. Further, its increased incidence over recent decades highlight its severity. Current clinical treatments include surgery and neoadjuvant tumor ratio therapy. However, challenges such as low specificity and resistance of such neoadjuvant methods hindered the development of osteosarcoma treatment. New strategies are needed to be explored. Reactive oxygen species-based therapy is promising for selective cancer treatments because first, high ROS level can trigger cell apoptosis. Second, due to the inherently elevated ROS level in osteosarcoma cells, they are more susceptible to further ROS upregulation. So in this case, we can identify a therapeutic ROS window where cancer cells undergo apoptosis while healthy cells remain unharmed. Selenium, a micronutrient in human body, is promising for the ROS-based cancer treatments because of its redox activity to generate ROS molecules. Compared to conventional drug, it is inexpensive and less prone to drug resistance. However, selenium still required a platform to control its intracellular delivery. Mesoporous silica nanoparticles are ideal nanocarrier because of their large mesoporous volume, nanoscale, good biocompatibility, tunable structure, and also functional surface for modification. So therefore, the overall aim of this project is to develop the Selenium-Incorporated MSN to upregulate ROS in osteosarcoma cells while sparing healthy bone cells, thereby enhancing the selective cancer treatments. To achieve this aim, we conduct 4 chapters. First is to develop the Selenium-Incorporated MSN. Here we have the first 2 research questions: how to incorporate selenium into MSN and which way is more effective. And due to the various oxidative states of selenium and the structure of the MSN, we found 3 modes to incorporate selenium into MSN matrix. First is to load the selenite ion on MSN mesoporous end surface. And second is to dope the selenite ion into MSN matrix. And the third one is to incorporate the elemental selenium nanoparticles with MSN layer. So in this study, we aim to investigate and compare the cooperation efficiency, release profile, and the therapeutic efficiency of different Selenium-Incorporated MSM to optimize the nanoparticle development. In the result, first, differential Selenium-Incorporated efficiency was observed among groups, and Selenium nanoparticle incorporated MSN had the highest selenium content compared to other two groups. Interestingly, 3 groups of Selenium-Incorporated MSN showed a redox responsive selenium release property while were pH independent. So based on the toxicity test, we optimized that the selenium doping and selenium nanoparticle incorporated MSN were more promising because they show higher anti-osteosarcoma ability while relatively low toxicity on healthy cells. Further, we confirmed that this selenium MSN could induce the ROS increase in osteosarcoma cells. This indicates the high potential of such selenium MSN to inhibit the cancer cell growth by ROS upregulation. Next, we continue to develop dose-loading MSN system for combination and targeting osteosarcoma therapy in Chapter 4 and 5. This idea was driven by another research question. Can co-loading system with selenium improve the therapeutic effectiveness by combination ROS upregulation? Recently, we found that the traditional anti-cancer drug, doxorubicin, was reported to mediate ROS generation by transferring mitochondrial electrons. So in Chapter 4, we aim to develop a selenium nanoparticle dose-loading MSM delivery nanoparticles that is suitable to enhance osteosarcoma therapy by combination ROS upregulation. In this study, we loaded dogs in the MSM Mesoporous and used the hyaluronic acid as the gatekeeper on MSM surface to control the dog's release, because HA is pH sensitive and also targets CD44 receptors. We first optimized the coating thickness that can affect drug delivery effectiveness, aiming to develop the most suitable MSM delivery system. And based on the morphology and the release profile of the nanoparticles, we optimized that the MSM with middle thickness HA coating as the best candidates for further research. And later, we invested combination effect of the dose loading of MSM by comparing with non-delivery system. The result indicates the dose loading MSM show enhanced cytotoxicity and combination ROS upregulation compared to the mono-delivery system, proving our hypothesis in this study. However, these nanoparticles still showed toxicity towards healthy cells at higher dose after longer period incubation. This raises another research question. Can we increase the selective toxicity on cancer cells in this system? We hypothesized that introducing extra glutathione responsiveness within the MSM-based delivery system enabled to achieve this goal. This is because osteosarcoma cells contain higher intracellular glutathione level compared to the healthy cells, which might accelerate the degradation of nanoparticles and also allow DOX release intracellularly. In this study, we introduced disulfide bonds between the MSM and HA coating to induce the glutathione responsiveness because of its higher sensitivity to the glutathione. First, in the result of the DOX and release loading, we found that the nanoparticles show the pH and glutathione dose response release property. And further, based on the in vitro cytotoxicity test, we demonstrated the dose-responsive nanoparticles enhance selective toxicity on osteosarcoma cells, proving our hypothesis. And moreover, nanoparticles differently upregulate ROS within cancer cells and healthy cells, which was the reason for the enhanced selectivity. In the Chapter 6, we continue to developing the bifunctional nanoparticles loading by ceramic granules for bone cancer therapy. This idea was inspired by a research question associated with clinical application. Can we control tumor suppression and repair bone defects caused by surgery in a single intervention? We hypothesized that bifunctional nanoparticle load in ceramics are promising candidates because, first, selenium doping MSN system developed in previous chapter can regulate effective selenium intracellular delivery to overcome accumulated toxicity in extracellular environments. Besides, turnable surface of MSN allowed multiple modification for binding on scaffold and the release. We here use beta-TCP as the osteogenic cues because calcium phosphate is the main inorganic component of bone, and it is biocompatible and osteoinductive. Moreover, the smaller size of the granules can allow to support irregular shape of the bone defect. So overall, this study was aiming to develop the selenium doping MSN coating beta-TCP granules that can provide on-demand nanoparticle release in response to acidic osteosarcoma microenvironments for anti-osteosarcoma and sequentially for bone repair. We use imide bond to induce pH responsiveness and alendronate to increase the binding affinity of nanoparticles on bioceramic granules. In the result, first, we confirmed that the surface modification enhanced the nanoparticle loading ability on the beta-TCP and also allowed more effective pH-responsive nanoparticle release. Later, we cultured the osteosarcoma cells and healthy cells with the nanoparticle loading granules in both acidic and neutral pH media to mimic the different pH microenvironments. We demonstrated that the granules show higher toxicity towards the osteosarcoma cells in the acidic condition, while sparing HMSC in the neutral pH media. This selective cancer treatment may be associated with the pH-responsive nanoparticle release we mentioned before. After releasing the nanoparticles for 5 days, we observed that almost nanoparticles have been removed from the granules. And here, the granules could also further enhance the ALP expression and mineralization of the HMSC. This indicates the potential of the osteogenesis for bone reconstruct. To conclude, I would like to highlight 4 take-home messages. First, selenium can be incorporated in MSN in various modes, and selenium doping and selenium nanoparticle incorporated are more promising for enhanced selective bone cancer inhibition. MSN can be the versatile nano platforms for dose loading, selenium and DOX for combination treatment through the synergistic ROS upregulation. And number 3, the pH glutathione dose responsive delivery system can improve the selective cancer inhibition of MSN by differentiating the ROS upregulation in cancer cells and healthy bone cells. And number 4 is the MSN loading bioceramic granules can provide pH-responsive nanoparticle delivery for bone cancer inhibition and sequentially activate osteogenic process of HMSC, demonstrated the potential of bifunctional granules for bone tumor treatments. Further, I would like to highlight the impact of this thesis. First, the selenium-containing MSN developed in this work provide great ROS upregulation ability, which can be extended to other cancer beyond osteosarcoma. Second, this thesis introduced innovative nanoparticle in engineering strategy, including ion drug incorporation and surface modification to enhance the therapeutic effectiveness of MSN. This strategy also shows potential for applications beyond cancer treatment, such as antibacterial and soft tissue healing. And third, this work proposed a new concept of bifunctional nanoparticles loading scaffold for local bone cancer treatment. This shows high potential to reduce the need for repeating clinical interventions. In the end, I would like to thank my supervisors, Sabine and Pamela, members of assessment committee, and collaborators, colleagues, and also funding resources. Thank you for your attention. Now I give word back to the proactor. Thank you.
Thank you very much. We will now start with the opposition. And the opposition will be opened by Professor van Griensven, Professor of Regenerative Medicine at Maastricht University.
Thank you very much. Dear candidate, thank you for the nice thesis. I really read it with a lot of interest and joy. And I also would like to, of course, congratulate the both supervisors. It's a very nice thesis. Of course, I have some questions. So I would like to start with chapter 3. So you test actually your selenium compound in SAOS 2 cells, which is osteosarcoma cells, and osteoblast cell line. You show less effect on the osteoblast, but it is done in separate cultures. Whereas in the bone, you have like normal osteoblast and osteosarcoma cells next to each other. So how do you envision that your therapy can really be for your osteosarcoma cells?
Highly esteemed opponent, thank you for your kind words and question. Indeed, this story is first aimed to validate the selectivity, therapeutic effective of these nanoparticles. And in this study, we only do the monolayer, the 2D cell model separately. But in the future, I will try to combine them together to see if it's possible to like first do the cell co-culture, and then to move to maybe more complex 3D cell culture using more complex model to test these nanoparticles.
So when you say more complex model, do you mean that you make like a more of a bone model with different cells, even beyond osteoblastic cells?
Yes, but in the current steps, I will first focus on combining the osteosarcoma cells and the HMSC together in the, like, for example, I will make the chip model and put in the one channel. But later, I will also think about maybe added the extracellular cells and the immune cells to increase its complexity of this model.
Yeah, because you can still think that even if you have like an effect on your osteosarcoma cells, also on the other cells, the selenium does have also an effect, right?
Yes, indeed. So that's why the difficulty part is to arrange the dosage, the dose administration of the nanoparticles, and also that's why I also want to highlight that in the chapter 6, I also use the nanoparticles loading scaffold. That's the local therapy aim to first to directly use for the resection bone defects, which first can remove the restant tumor cells, then starts the bone regeneration process. Because even there's some healthy cells being effective, we can use the further osteogenic cues to maintain it in the latest.
What was interesting that you just mentioned, you said the dose. When I read your thesis, you actually used different doses on the healthy bone cells, on the healthy osteoblasts, compared to the osteosarcoma cells. The osteosarcoma cells had also higher dosages. Don't you think you should also test a higher dosage on your normal osteoblasts?
Actually, I think in the thesis, I used the same range of the nanoparticles concentration. And the aim is we want to see we want to figure out one concentration range that can kill the cancer cells, but do not harm the normal cells. That's our aim.
Okay, because I thought you used a little bit different, but that's fine. When you look at your nanoparticles, they have silicate, right?
Yeah.
So silicate is also known to induce osteogenesis, also have like an effect on mineralization. Don't you think that it can be actually detrimental to add that to your osteosarcoma, because thereby you can actually stimulate your osteosarcoma instead of inhibiting it?
Yes, that's. Thank you for the question. Indeed, silicon can generally also induce the osteogenesis process, but compared to the selenium, the toxicity, it will be like more smaller. And the aim of this therapy is we want to first to kill the cancer cells in the faster way, in maybe maximum 3 days, and then starts the osteogenic processes. So I know I want to choose like high amount of selenium as possible to first kill the osteosarcoma cells. But in this process, the silicon cannot like regenerate or like cure the osteosarcoma cells.
Do you think it's able to really tune those kinetic pathways?
Yes, because like the effects from those two ions are really different. The selenium is really toxic compared to other. And
but time-wise, can you change it time-wise? So because you said the selenium is there, but also the silicate is there, can you really have your selenium first to kill the osteosarcoma cells and then the silicate?
For this project, I think the silicon and selenium will degrade it at the same time because it's the selenite is inside the MSM, and it will degrade it based on the glutathione, and mainly the whole structure will collapse. But I assume the selenium will first go into smaller, much smaller size, like in the iron structure, and the rest of silicon will also like maybe degrade slower. So it can be the reason. And yeah, also I want to mention another thing. If I do not have the selenium, the MSM will keep stable in the both acidic condition because it only can be degraded in higher pH.
And when we then go to chapter 4, you actually put there a shell of hyaluronic acid around it.
Yes.
Does that influence the kinetics of your selenium and of your silicate then?
I think that's because the coating is aimed to control the DOX release, and it can be penetrates based on its pH responsiveness, and also the glutathione is smaller chemicals. It can penetrate into the nanoparticles, but the time will be a little bit longer. So in the result, we can see the toxicity. It will be a little bit decreased, based on the coating. Mm-hmm. But it's also promising because we can control its the selenium release, and we can also include another additional drugs to make sure we can both decrease both of their dose and then make the similar or even higher effects.
Mm-hmm. When I look at the hyaluronic acid shell you made, you say also correctly that it is going to the CD44 receptor. A lot of cells have CD4 receptors. So combining now your ideas in chapter 3 and 4, you spoke about selectivity. How selective are you then when you have this hyaluronic acid core?
Actually, the hyaluronic acid is in the beginning, we aim to use this HA as a target ligand for cure the cancer cell but without harming the normal cells. But in the end, we figured out both SALS2 and HMSC showed higher CD4 receptor expression. So in this case, our aim is to use the HA as the gatekeeper, and then to make sure this coating can allow the nanoparticles to enter both cells to activate the ROS effect. And the selective treatment is mainly associated with the ROS upregulation, because I mentioned before, the ROS level are differentially showed between the cancer cells and the HMSC. It can, ideally, it can increase the ROS in the cancer cells over the threshold and start apoptosis, but without hurting the normal cells. So that's the main aim.
Okay, then a last small question. So in the chapter 4, you used actually 2 different osteosarcoma cell lines.
Yes.
And they reacted actually differently. They had different ICs. Is that then depending on the HA receptor?
No, I think because I also checked the cell uptake experiments, it showed the similar cell uptake. And I think mainly, different cell, because those are all the cell line, they maybe show different sensitive to the selenium and also the DOX, because I introduced 2 parameters.
Okay. Thank you very much. I'm happy with the answers and give back to the pro-rector.
Thank you.
Thank you very much, Professor van Griensven. The opposition will now be continued by Professor Santos, Professor of Medical Engineering from the University of Groningen.
Thank you very much, Prorector. So, dear candidate, I also read your thesis with great interest, and congratulations for this beautiful work as well. And I extend the congratulations also to the supervisors as well. But I also have some questions to you, of course. And my first question is actually related with that picture that is behind you. And the drawing of what it resembles a tennis ball. And my question to you is that, do you think that, is it closer to a tennis ball or perhaps more a golf ball? What is your opinion?
Highly esteemed opponents, thank you for your kind word and questions. Indeed, because first I designed this based on my preference. I play tennis, so that's why. And also the golf ball is more close, like in the look, it's more close to the MSN, indeed. But it's I want to highlight. First of all, including my interest, and also I want to highlight that I use this record to introduce the nanoparticles to cure the osteosarcoma.
Okay, very good. Thank you. I will have to continue on your drawing skills as well. So in many of your figures throughout the thesis, you tend to draw your silica particles and your drug that is actually on the surface of your silica. However, I believe you mean that is loaded. Is that correct?
Yes, indeed. Actually, I want to distinguish these two parts. The dogs, I think I want to distinguish the location. First, the dogs maybe can more close to the surface because it's loaded in the Mesoporous. And but for some nanoparticles, I have the silicon nanoparticles in the core, right? So that particles, it shows a smaller Mesoporous volume. So I want to just say that the dogs can maybe also load it on the surface. So it's
okay. So if you go in your page 84, when your figure 1, so you mean that the your ducts is closer to the surface rather than in the pores?
Sorry, which?
Page 84.
84. Okay.
In your schematic figure 1.
Oh, yes, that's maybe, thank you for the correction. Indeed, it's ideally it should be in the Mesoporous, but because I made the nanoparticles a little bit smaller, and I want to make it more clearly to see the dogs. Yeah.
Okay, clear enough. Yes, I've been working for 20 years in the Mesoporous materials, but I was wondering how you could stick it to the drugs on the surface. And then also in the same page, actually in the page 84 and 85, you mentioned twice hyaluronic acid. In one case you mentioned coated, and in another case you mentioned conjugated. So what is the difference between both? And I believe you meant one of them.
Yes, I thank you for the question. Indeed, and the correction. Indeed, I've mainly focused on the coating, because I used mainly all the carboxyl group in each unit of the HA, and it's like the coating around. It's different from other researchers directly using the conjugates, indeed, like the ligand on one side. So I think it's mainly for the coating.
Very good, thank you. So the chemistry that you use is very elegant. I really like the way you put your selenium nanoparticles and then you build up the pores around. I think that is very, very unique, and I really enjoy it. We have been doing like separately, but you managed to put in one single structure, which is really cool. And then you did the complex system with hyaluronic acid. So my question to you is that how actually you are controlling the release of your drug. So I know that you have your coating, and then you have, or you have your conjugation of the hyaluronic acid, and then if you have your loaded drug. But how precisely can you actually control? Do you ever achieve a perfect conjugation or coating of your particle?
Thank you for the question. Indeed, for here, I only controlled the drug delivery, drug release by using different thickness of the HA coating, by adding different amount of HA in the system. That's the way. And also we can also add a different amount of dogs when we co-immerse the nanoparticle with the dog solution. That's another way. And but for other, I think
Yeah, because I mean, if you look to your page 95, I was very much impressed how your slow release you can achieve, and I would think that in this kind of conjugation you have plenty of space for the drug to diffuse through your system in order to get out. So, what is the mechanism of that makes the drug to be so slow, or there is any interactions between the drug and the polymer?
I think let me think. The dogs can be more like connected with the Mesoporous, because the dogs is positive, has the amide group, and it can connect it to the carbox group, the OH group in the Mesoporous, so it's like more stable. And this picture, I want to see the pH responsive dogs release. The mechanism behind it is, I'm still not sure, maybe due to the pH responsive of HA, or maybe due to the pH response penetrate of the HA. It can penetrate faster through the HA hydrogen coating in the more acidic environments. That's the part.
Okay, yeah. Okay, thank you. Very interesting. So going back a little bit to your chemistry, so in page 76, you have huge reduction on the surface area of your particles. Yeah. When you have the selenium nanoparticles. Do you think that is a big problem if you consider the application of your particles? If you compare with the porous materials itself, you usually have a very high surface area. But then when you do it with your selenium nanoparticles, there is a drastic reduction. You think that is a big problem there?
I think that's... thank you for the question. Indeed, because I think the specific surface area is related to the size somehow. And for the Selenium nanoparticle incorporated MSN, it's a little bit bigger indeed, because it's connected to the nanoparticle inside. And it will, but I think it can slightly affect the cell uptake maybe, but the size range is from the previous, the selenium doping one is around 80 nanometers. So the change is not so big. I think the effect will not so higher.
Okay, very good. And then you did your selenium nanoparticles in organic solutions, right?
Yes.
So do you think it could be done in green-based, more greenish?
Sorry.
Like water-based? Do you think you could ever done it in water-based solutions instead of organic-based?
I think. Let me think. Yeah. It's possible because I made when I doped the selenium, we have two solutions. One is the organic.
In the last part where you have the core as the selenium nanoparticle.
You mean the selenium doping one?
Yes.
I think it can be also used in water.
It can, yes. We just developed a method actually to do it in water.
Yes.
So it's beautiful. If you can make it in water, then it becomes much more applicable for clinic. And if I may, the last, do I still have time?
Very short.
Very short. I was asking the parent if to read the proposition number 8.
Clinical translation of MSNs for tissue regeneration requires precise design to ensure batch-to-batch reproducibility, tunable and safe biodegradation through evaluation of biological interactions. For instance, immune response, hemotoxicity, organ accumulation, and robust preclinical validation.
Thank you very much. So a very quick question. For a quick answer, how do you think you can improve the batch-to-batch reproducibility of the systems that you have mentioned in your thesis?
Yeah, thank you for the question. Indeed, for now, I found the reproducibility of my nanoparticles, the selenium doping one will be the best because it can reproduce based on our old protocol, similar to the pure MSN. For the maybe for other two, for the another one, Selenium-Incorporated MSN, I think I need to maybe change a little bit for the selenium amounts and also the CTAP, the like dosage, and also the TILs, the amounts to make sure it's reproducible.
Okay, thank you very much. I give the word back to the prorector.
Thank you, Professor Santos. The opposition will be continued by Dr. Español Pons from the Universitat Politécnica de Catalunya.
So, thank you very much. First of all, it's an honor to be part of this jury board. And dear candidate, I want to congratulate you for the excellent thesis and make extensive these congratulations to both your supervisors as well. So I have some general questions. And my first question is based on chapter 3, where you try to optimize the mode of selenium loading. And you beautifully use these 3 different methods. So my question is, when you try to compare the selenium loaded with the selenium DOP modes, you see that in the, I think it's in figure 6, in page 68, you'd see that the ROS release, the ROS production, it was quite similar in between the selenium loaded and the selenium DOP, yet the cytotoxic effect on the selenium load was way higher, no? So what was the explanation? What do you think is going on?
Okay. Highly esteemed opponent, thank you for the question. Indeed, I think because in this one, I only want to confirm those 3 nanoparticles can induce the ROS increase. But I only choose one time point. Maybe the selenium doping MSN can increase the ROS level in the early stage. But after I wait a little bit longer, the ROS will be vanish. Yeah, it's not stable. So it's a little bit tricky to measure this ROS data. So in the future research, I think if I also want to investigate the ROS assay, I will pick different time points to see the difference. Maybe in the later, this is 12 hours, maybe I choose the 6 hours, it will be higher compared to others.
Okay, so it changes quite a lot, the ROS.
Yeah, over time, yeah. And also the ROS because generally based on the literature, they also found when we treated the cells with the H2O2 and the ROS increase over time and then decrease. It's like the peaks, they have the peaks.
Okay, then regarding the condition of the selenium DOP and nanoparticles, I think you also made an additional type of nanoparticle in which you add the disulfide bond.
Yes.
And that was, as I understood, to increase the degradation of this particle. So I believe that you wanted to have some more release of this selenium and then get more ROS response and therefore more cytotoxicity. But when you look at the cytotoxic response,
yes,
it wasn't superior to the DOP non-degradable condition. So what's your explanation to?
Yeah, thank you for the question. The thing is, the selenium doping MSN can directly sensitive to the glutathione, and it's really fast because selenium can be reduced by the glutathione and changed to the H2, the hydrogen selenides. And but if I introduce the disulfide linker, it will also consume more glutathione. So it's difficult to compare because I think after adding the disulfide, I think it's not really necessary. But I also want to put this result in the thesis to see how affects. And normally, because in the beginning I want to introduce another ion, then we need the disulfide to increase this degradation. But when I use the selenium, it's not necessary. So that's the reason.
Okay, okay.
Yeah.
Now that you say that you wanted to introduce another ion, what was that ion?
We can try maybe other zinc or something, or magnesium, which can also introduce regulate ROS, but that's another another story. That's not the focus of this thesis.
Okay, that's curious on this. Yeah, and also a very general question is, at the end of the day, I'm not really working with this topic, so I was curious to know whether you really need to have the release of the selenium dope in order to have this cytotoxicity, meaning that could it be that GSH could enter into these nanoparticles and then produce the ROS species, or do you need the nanoparticle to be degraded for this effect to be seen?
You mean is the, thank you for the question. Yeah, I think they need the selenium nanoparticles indeed. When the mechanism ideally is nanoparticles enter to the cells and through the lysosome and they match the glutathione, and glutathione can degrade reduce the selenium, and then they can, this process also involved with the oxygen, and they can oxidize the oxygen into oxidized ion. That's one molecule of the ROS. So that's the process. It's a little bit complex. Maybe I can show you the figure in my chapter 2. That's more clear. Let's see, the page 20 and the figure 2, number figure 2, and figure 2A. That's the base mechanism for the selenium, and it needs the reductants, the glutathione, and also the oxygen somehow. So that's, thank you.
On the next chapter, it was very nice that you added also, you tried to see the combination therapy between doxorubicin plus the selenium nanoparticles. It was beautifully done. And then on this chapter also you investigated, as it was also mentioned by the other professors, right? The addition of hyaluronic acid. And then you put hyaluronic acid playing with different types of thicknesses, low, medium, high, and also playing with the molecular weight.
Yes.
Yeah, so my question is, I think I've read in the thesis that you were playing with molecular weight in order to facilitate the uptake.
Yeah.
So what's the, let's say, how molecular weight can control internalization?
Thank you for the question. Indeed, based on the literature, we found different conclusions. Indeed, some papers shows that higher molecular weight of HA can accelerate the cell uptake. But in our result, we found that the lower molecular weight can show slightly higher cell uptake. I think that may be due to the like HA chain. Because if I use higher chain, it will overlap and it will maybe hide some domains that can attach on the cell membrane. So that may be the reason. And that's my answer. Maybe, yeah.
Okay. And then you also, with regards to internalization, how do you know whether really nanoparticle gets inside the cell or it gets absorbed on the cell membrane?
Yes. You mean the cell? Yeah, because based on the cell uptake experiments, we can observe that we use two nanoparticles to check the cell uptake. First is the nanoparticle with the DOX, because DOX is autofluorescent. Yeah. We can use it to check the nanoparticles inside the cells. If the cells fully fluorescent, we can think it's uptake. But you think it's still on the membrane.
Could it be that it just absorbs on the cell membrane? It would give you the same.
Yeah, that's the good point, because I think. I cannot understand this, but we didn't do this experiment. But I think in the future, I can also add a control to maybe block the membrane attachment, or we can block the cell uptake parts, and then see if the nanoparticles can also enter to the cells, if there's still some like signal. Mm-hmm. And also, I now remember when I observed the cells in the microscope, not the fluorescent, we can also see some, I think the shrink of the cells. It's associated with the uptake because the nanoparticle already starts its effect. inside the cells.
Okay, okay. Maybe it's also considering like trying to stain the cell membrane. I don't know
Yes,
whether that's
yeah, that's the better way. Yes, I know.
Yeah. So I thank you very much. It's really indeed a very nice thesis. Thank you.
Thank you very much, Dr. Espanyol. The opposition will be continued by Professor Willems, orthopedic surgeon and professor of integrated spinal care at Maastricht University Medical Center.
Yeah, thank you. Thanks for the invitation and my congratulations to you and your promotion team. Also my congratulations on obtaining your Coaster Talent Fellowship, so you can prolong your nice work. I'm a clinician. I have some questions about translational aspects, and I basically want you to explain to a clinician what you've been doing. And I would like to know if you have an environment with mixed osteosarcoma cells and also normal cells, how do these nanoparticles find the right cell? How does it get there? Because it's all in a mixed area. And if they can find those cells themselves, why isn't it possible to inject the nanoparticles so they can search for the osteosarcoma cells?
Highly esteemed opponent, thank you for your kind words and questions. Indeed, for the aim of this project is to use ROS therapy, and the ROS therapy is not aimed to selectively target the cells. So if I have the environment with the cancer cells and the normal cells, the nanoparticle can enter to all of them, and based on their differential ROS level, they can kill the cancer cells based on the concentration of nanoparticles and not slightly harmful to the normal cells. That's my aim. So that's the therapeutic window I want to arrange.
So they only reach the cells from local diffusion where they're applied. That's basically it, or not?
Yes. And for your later question for the injectable, yeah, the nanoparticle can be intravenously injectable, but my focus is more to the bifunctional composites. I want to choose the local therapy, like by combining nanoparticles with the scaffold as implants directly after surgery to to avoid more systematic toxicity.
Yeah, and that's interesting. So, what you described in chapter 6. How do you then determine the right dose if you have defects are all variable and in surgery, and sometimes vascularity is different. Sometimes people need post-surgical radiation. How do you determine? How do you think it can be determined to put in the right size scaffold and the right dose to get your goal?
Thank you for the question. You mean for the implant part or only the nanoparticle part? Implant part, okay. The implant part, I think that's why before we go to the clinic or in vivo study, I think it's better to have another more real or complex model to test this. And when we have this chip model, which can provide high throughput screening, we can try different amount of either the scaffold with the nanoparticles, and we can control the nanoparticle loading on the scaffold or the granules. Then we can make a difference for the dosage or the concentration. Yeah, then in this case, we need a lot of data, a lot of variables. That's why we need fast screening tools to analyze.
Yeah. And then to go further in it, maybe a 3D models, or are there also animal models for osteosarcoma you can use?
You mean the animal? Yes. Thank you for the question. For me, I do not have any idea for the animal model setup, but I think it's quite difficult because for now I focus on the primary osteosarcoma. The easiest way is we can directly inject the tumor cells in the bone area to make a similar tumor structure as the animal model. But if we need really to mimic in the real condition, we need to at least to mutate the gene and let it grow by itself. That's another idea, but that's more complex.
Yeah. How do you see to get this to clinical practice? What steps are further needed to get it there, do you think?
First, of course, here is only the first step, right? The very first step, and we also need to, that's what I described before, we will develop a more complex in vitro model to evaluate more detailed parameter of this biomaterials or the bifunctional granules. And then after this, when we found one parameter that's suitable to further research, we can go for the in vivo study, and later we can go for the clinical trial. That's the path I plan, but it will take maybe more than 10 years, I think.
Still work, improve, in advancement. Okay, thanks. I'm satisfied. Back to the prorector.
Thank you.
Thank you, Professor Willems. Then we come to the last opponent, Dr. Tamasebi Begani, Assistant Professor in Microengineered Biomaterials and Bottom-up Tissue Engineering at Maastricht University.
Thank you very much. Dear candidate, I also congratulate you on completion of your thesis, also your supervisors. I really enjoyed reading it, but I still have a few discussions that I would like to conduct here. Maybe I start by chapter 5. So you, of course, in chapter 5, develop your formulations, apply them to different cell types, tumor and healthy, and you see differential responses. But you also do see differential responses between the two healthy cells, so the HFOP cells and HMSC cells. You mentioned this a few times, but I would like to ask you one more time to describe what is the mechanism between these differential responses between the two healthy cells.
Highly esteemed opponent, thank you for your kind word and the questions. Indeed, it's really not unexpected, but surprise results for me, because in the beginning I think it will be similar. I hypothesized the reason because the HFOB cells is like a genetic mutated cell line, and it shows higher metabolic activity. So it's maybe more sensitive to the dog's effects. That's why because we also test the dogs can kill the HFOB cells faster. So that's why now I focus on the HFOB, or maybe later I will choose another primary cells, maybe osteoblasts, to double check, because in the beginning I want to each have two candidates to confirm my hypothesis.
Excellent. You also exactly mentioned this answer in your thesis, that HFOB cells, they are immortalized, so they exhibit higher metabolic activity and lower antioxidant defenses. Yeah. So I would like to challenge you. Can you think about other normal, natural cell types in bone that they have exactly the same characteristic, high metabolic activity and low antioxidant defense? Can you name a few of the cells that they might be in bone with the same characteristics?
You mean the cell line, or the
I mean the normal cells.
Normal cells.
Yeah.
Osteoblasts, you think, you mean the old type of cells in the natural? Okay, I get it. Like, for example, osteoclasts definitely have dual amino system, and osteoblasts, and maybe the astrocytilian cells to introduce the blood vessel vascularization, and HMSC, of course, it comes to when there's have a bone defect, it will be more HMSC to recruit to be there for proliferate. And also I read one literature, they mentioned like pro-osteogenic cells, like between the HMSC and osteoblasts, it can be like the one passage of the cells too.
Yeah. So I was really interested in your hypothesis, actually. So I read a few papers and exactly came to the same responses that you actually gave. So indeed, one of the highly metabolic cells with a lot of sensitivity to these kind of compounds is actually osteoclast. So what do you think would be the effect on of your formulation on osteoclasts? Are we not going to destroy complete balance in bone? Because osteoclasts are also very important to keep that bone regeneration and homeostasis in the healing bone. So what do you think would be the fate of these cells in response to your formulation?
Okay, thank you for the question. I hypothesis that of course, the selenium nanoparticles in developing this study will also inhibit the osteoclast activity because the selenium will kill every cells based on the ROS level. But my aim is because the osteosarcoma cells mimic the osteoclast cells type when it's be there, so it can accelerate the bone resorption. So when we either kill the osteoclast or the osteosarcoma cells, we can inhibit this process. And after we remove completely the osteosarcoma cells, then we can have the more homogeneous or regular homeostasis of the bone, and then the bone can also regenerate by itself. So later the balance will be recovered, and it will maybe the osteoclast can proliferate back, and also we can also include these cues. We can add in more inflammatory factor to allow the balance to make sure this balance.
So that's
a really nice suggestion indeed.
So you will make your formulation more and more complex to compensate for all of these effects.
Yes, that's actually the first step for the research. But in the end, I will, if we go to the clinic, I will try my best to maybe remove the unessential parts and
Okay. Yeah, so continuing the same more complexity in the models, I would like to ask one of the gentlemen in the Paranev team to read proposition number 7.
Advanced 3D in vitro models are required to more rapidly and accurately assess biomaterials for tissue regeneration, surpassing the constraints of traditional 2D and animal models, such as physiological relevance, high cost, and ethical concerns.
Thank you. So you, of course, want human-based to increase relevance, right? You also want your models to be inexpensive, ethical, but you also emphasize on the word physiological. So I would like to ask you, in your opinion, what would be physiological in these contexts? If you want to study the effects of a biomaterial that is at the same time regenerative, but also anti-cancer, what model do you have to develop? What are the essential biological, structural, material aspects that you have to have in this model, sorry?
Okay, thank you for the question. For now, I will continue another project. I'm mainly focused on develop organ-on-chips model using microfluidic technique, and it contains the bone defects in the middle chamber, and also it can mimic the 3D co-culture in the channel. That's what I described before, and that's the first step indeed. And it's not. The aim is to fast screen the biomaterials, but later I think we can design a little bit more complex design pattern of the chip. Then we can include different type of cells to mimic more real condition of the bone's microenvironments, or even the osteosarcoma, the cancer infected bone defects microenvironment.
And which cells, if I may ask you, in your opinion, is essential to actually be there in that organ-on-chip model?
I think for at least 4 cells, because I have cancer cells, and the HMSC, and the osteoclast, or more the immunocells, and then the epithelial cells, maybe, to introduce the vascularization. That's the.
Thank you very much. So if I have time, I will go to another question from chapter 6. So we heard a little bit about the relevance of these type of materials for bone regeneration and cancer therapy, but these are in the form of granules. We did see the release profile from these materials for 14 days in your thesis, but my question is that how long do these materials last in the body, and how long do you think is important that these materials stay in the body?
Thank you for the question. I also explained the aim of in previous the anti-cancer parts should be fast in shorter periods. So I want the nanoparticles to be released in the faster, maybe at least maximum 1 week. Then we can start the procedure of the bone regenesis and because the microenvironments after the cancer removed, the microenvironments of the bone will be neutral. So the calcium phosphate can stay there, and it can use as the substitute to either support the bone defect and also to activate the osteogenic differentiation of the other the HMSC, then to build the bone formation. That's my ideal idea, but it needs to somehow some optimization, and also maybe we can introduce some gel to support injectability, and later to.
And do you have any idea of the degradation time of your TCP granules at this moment? Like how long it takes until they are completely dissolved?
For my idea, I think I can do this experiment, but in the hypothesis, I think it will not degrade so fast because it's centralized and it will stay there for
few weeks or months. Yeah. Okay. Thank you very much. I'm also satisfied with the answers.
Lei He, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberations and our return in this room.
Thank you.
Please be seated.
Lei, the degree committee here present has assessed the quality of your thesis and of your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor van Rijt is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Lei He, the degree of doctor and grant you all the rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. Dear Dr. He, dear Lei, it is my great pleasure and honor to be the first to officially call you doctor and to congratulate you on this tremendous achievement. You successfully published your work on the development of selenium-based nanoparticles for osteosarcoma treatment in 4 excellent research papers and 1 review article. These contributions have now culminated in the beautifully written thesis that lies before us today, an achievement you can be truly proud of. Especially when we consider your journey. You arrived in the Netherlands in April 2020, right in the middle of the COVID lockdowns. Pamela had recruited you through the MDR consortium, and you arrived to find the country and our lab closed. But instead of waiting passively, you dove into literature research, summarizing your findings in detailed Word documents that you diligently sent to us. We had weekly online meetings to discuss your ideas. Already then it was clear that you were highly motivated, full with ideas, and scientifically curious. When the lockdown was finally lifted and we met in person for the first time, I remember thinking, wow, you're so tall. Until that point, I had only seen you on the screen. As soon as you were allowed in the lab, you got to work. The project was a true interdisciplinary collaboration, merging Pamela's expertise in osteoinductive calcium phosphate ceramic, my background in nanomedicine, and your own experience with selenium-based systems from your master's research. The goal to develop bifunctional nanoparticles that could both kill cancer cells and support bone regeneration. You proposed using selenium nanoparticles for ROS-based therapy of osteosarcoma, and your work showed how critical nanoparticle design is to the therapeutic outcome. You always brought enormous energy and enthusiasm into the lab. This resulted in a tremendous amount of data, reflected not only in the main chapters of your thesis, but also in these substantial supplementary sections. Over the years, I've seen you grow remarkably as a scientist. You were always eager to complete every data set and often dove deep into the details, sometimes conducting more experiments than were strictly necessary. The challenge was never the lack of data, but rather how to shape it all into a coherent and compelling story. Your curiosity often led you to explore new ideas even before we had a chance to discuss them in our meetings. As your supervisor, I regularly encouraged what we in Dutch call een stap op de plaats, a moment to pause and reflect. But your passion for science usually took over, and you simply couldn't resist testing new ideas in the lab. While this exploratory drive sometimes left us with more data than we could easily structure, it also showed your creativity and dedication. Over time, I saw you grow in focus and planning. These days, you come to our meetings with a clear plan, grounded in solid rationale, well-defined goals, and logical next steps. Combined with your technical skills, efficiency, and strong work ethic, this growth in scientific reasoning and communication makes you, in my view, a truly talented researcher. Others have recognized this too. Recently, you were awarded Best Oral Presentation at the MBTE annual meeting, and just last week, you received the COSRA Postdoctoral Fellowship. This allows you to continue your work at Merlin, now in collaboration with Ninofar, who is also here today as a committee member, developing cancer-on-chip models to test our bifunctional biomaterials. A new and exciting direction in your research. While reading the reviewers' comments of your COSRA application, one line made me smile. A 10 out of 10 for enthusiasm and passion, but answers could sometimes be more to the point. I couldn't help but laugh because it describes you so well. It has truly been a pleasure to have you in the group. You are always positive. I honestly don't think I ever heard you complain. You're kind, respectful, and welcoming to newcomers. You brighten our lab and Merlin as a whole with your big smile and cheerful presence. Whether it's helping someone clean up a spill in the lab, even if it wasn't yours, or just lending a hand when needed, you've shown great generosity and team spirit. The start of your time in the Netherlands was not easy. The COVID years were isolating and it was difficult to build a social circle. But looking at the room today, I see your wife, friends and colleagues who have come to support you. It's a beautiful sign of how far you've come and how much you've grown both professionally and personally. Before I close, I would like to sincerely thank Pamela for being so actively involved in Lei's supervision. Even with your incredibly busy role as a rector, you've always taken the time to stay engaged, to listen to updates on Lei and other students' projects, and to offer sharp, thoughtful, and constructive feedback. Your support has been incredibly valuable throughout this journey. I also want to thank all the collaborators who contributed to this work, as well as the Assessment and Promotion Committee for their time and expertise. A special thank you to today's chair, Martijn van Giensven, for ensuring that everything ran so smoothly. I would like to warmly thank Professor Helder Santos for traveling from Groningen to be with us today. It's a true honor to welcome you to Maastricht, and I hope we have a chance to visit you in Groningen soon. A heartfelt thank you also to Associate Professor Montse Español, who came all the way from Barcelona. We met many years ago at a conference. I don't remember which one, but I do remember how easily we connected and the lovely conversations that we had. It's wonderful to have you here today. And thank you, Professor Paul Willems, for your presence and valuable comments, both during the defense and in the review process. And finally, thank you, Nilofar, for your scientific expertise, your valuable feedback, and the exciting collaboration we are now building together in Lei's postdoctoral project. I look forward to seeing how this joint effort develops. Dear Lei, congratulations again on this well-deserved title. Before I finish, I would also like to extend my congratulations to your wife, your family, and your friends here and watching online. Enjoy this special day, you've earned it. I'm certain that you will have a bright future ahead of you, and I wish you all the best in your career and in your personal life.
Thank you so much.
Dear Dr. He, also on behalf of Maastricht University, I would like to congratulate you with the degree you have acquired. Of course, I'd also like to congratulate your wife, your family, friends, colleagues present here, but probably also present online. They have undoubtedly supported you on your way here to a strange country, but I hope you feel by now at home a little bit. I'd like to congratulate your supervisors with the successful end of this PhD project. I'd like to thank the committee members for their contribution, especially Professor Santos and Dr. Español. Thank you for coming all the way to Maastricht. Maastricht University really appreciates your contribution. And then I wish you a lot of success with your further career. And I understand it starts here in Maastricht. You never know where it ends, but for the coming years, you be around. I think it's now time to relax, and I end this academic ceremony.
Thank you.